All right. Good morning, everybody, and welcome to the third lecture on uncertainty in computational geometry. So in the first lecture, I gave a big overview. In the second one, I talked about how to compute lower and upper bounds on geometric measures. And in this lecture, I want to talk about pre-processing. So it's a different paradigm, maybe, of what you can do in the presence of imprecision. So let me first explain a bit what this idea is about. So in this pre-processing paradigm, the idea is that, well, even if we have uncertain data right now, maybe it's not always going to be uncertain. Maybe later we will be able to measure better where our points are, or for some other reason we get more precise information later. And the question is really, okay, given that I now have imprecise data, and maybe later I get precise data and I want to compute something on this precise data, how much of this computation can I already do now? Okay, so we're given in the beginning a set of regions. Like here, and these regions are imprecise points, so every region contains 1 point, same model as before. And later, maybe soon, we get another set P, and P is the actual points. Okay, so P is 1 point inside every set. And what we want to do is compute some property of P, maybe the Delany triangulation or minimum spanning tree or convex hull or whatever. Okay, so we want to compute this, maybe a triangulation of the point set. And one way to compute it is, of course, to just wait until we have P and then use our favorite known algorithm for computing this structure S of P. But maybe this algorithm is somehow slow. So, for example, if we want to triangulate the point set, it's known that we cannot do this faster than n log n time. And maybe we don't have that time when we get P, because when we get P, we really quickly want to know S of P. So how much of this computation can we already start doing right now? Okay, so the idea is that maybe we can compute some sort of intermediate structure. Let's call it H. So H of R is some sort of structure. I don't know what it is, but it's something that we can compute from R that helps us compute S of P faster than without this structure. Okay, so once we get P, we want to compute S of P using H of R and P. So we want to find an algorithm here that gives us S of P given these two things, which should be faster than this algorithm. All right, that's a general idea. And there are several results of this type. So some of them are known for triangulations. There's an algorithm by Held and Mitchell that says you can compute the triangulation of a point set in linear time after you compute the right kind of preprocessing, whereas doing it directly would cost n log n time. Held and Mitchell do this for unit disks, and we extend this algorithm to arbitrary polygonal regions or even arbitrary regions in a plane, as long as they're disjoint. And this algorithm, this result, I will talk about in detail. For Delany triangulations, you can also do the same thing, but not for arbitrary regions, only for disks. And there are also some results that say you can not compute a structure in linear time, but still faster than n log n time. For example, convex hulls and onions, and I will also talk about the onions in a bit more detail later, and maybe if there's enough time I'll talk about the Delany triangulations as well, but I'm not convinced that there will be enough time. Okay, so is the paradigm clear? So then let's talk about how do we solve this problem if we want to compute a triangulation of a set of points. Okay. So we are given this set of regions in the plane, and I'm going to assume that they are polygons and that they are disjoint. So something like this. Okay, and then according to the paradigm, later I will get 1 point inside every polygon. We want to compute some intermediate structure H. And then later, we get 1 point per region, and the idea is that if we use this magic structure, we can triangulate the points in linear time. Okay, that's the goal. And the question is, of course, what is this structure H, and how do we compute it, and then how do we compute the triangulation? Okay, so before I'm going to solve this problem, I'm first going to solve a different problem, which turns out to be useful. So the different problem that I want to solve is the following. Suppose I am given already a triangulation of a set of points in the plane, but the points have two colors. I have red points and I have blue points, like this here. I hope the color is a bit visible, but this one is, for example, red and this one is blue. So I have a triangulation of red and blue points, and what I want to do is get a triangulation of only the blue points. Okay? So some blue points are already connected, like this one, and some are even already forming triangles, so that's great. I can just use them in my triangulation. But some blue points are not connected because there's red points in between them that are blocking the connection. And what I want is to get rid of all the red points and their connections, and then have a triangulation of the blue points. Of course, if I just throw away all the red points and their connections, then I may have just isolated points, and triangulating them would cost 10 log n time. So can we still do this in linear time? Well, the answer is yes, we can do this, and I'm going to tell you how. So the main idea of how to do this is, well, suppose that we have a constant degree red vertex, like maybe this vertex is red and it has only 1, 2, 3, 4, 5 edges, that's constant. Or this one is red and it has only 4 edges. So what we can do is just pick some vertex of degree at most 5. It's known if a triangulation is a planar graph, so there must be a vertex of degree at most 5. We can remove such a vertex, like this one has degree 5. I can remove it in constant time. I get a gap of constant size. I can retriangulate this gap in constant time, like this. And now I have a point set with one fewer point. So if I just do this and I spend constant time per point, of course I can remove some set of points in linear time. Takes constant time per red point. Of course, there's a slight problem here. So I said I want to remove a constant degree red vertex. And I say there is always a degree of at most constant degree. But of course, maybe all the points of constant degree are not red. That's possible, right? Maybe I have something like this, where I have lots of blue points and there's a bunch of red points that are still in there, and all the red points have high degree. Well, then this approach doesn't work, because if I now just remove this red point, then it takes maybe linear time, and I have to retriangulate the gap, and this takes too long. Okay. Of course, we cannot say, well, then let's just pick a blue point of constant degree and remove that and retriangulate, because then later I have to insert it again, and it's not so clear where I have to reinsert it. So the solution to this slight problem is to maintain not a triangulation of the points, but a pseudo-triangulation. All right, so pseudo-triangulation is a subdivision of the plane into pseudo-triangles. A pseudo-triangle is a polygon with exactly 3 convex vertices. So this is a pseudo-triangulation, maybe. So in general, a pseudo-triangle looks like this. Something like this. Okay, so it's a polygon which has 3 convex vertices, just like a triangle, and then there's a bunch of concave vertices in between. The kind of pseudo-triangles that we need are only pseudo-triangles that have 2 straight edges between their 3 vertices and 1 concave chain. So at every red point, I maybe have some edges that go to other points and then in between I have some, I may have some concave chain that consists only of blue points. And the idea is that this way we can ensure that there is always a constant degree red point. Okay? Because I don't need too many edges in between to all of these blue points. But I do require that I have an edge between every pair of red points, or every pair of red points that was connected in the triangulation. Okay, so this is the main idea. Okay, so if we have some sort of a pseudo-triangulation like this, then I have constant degree red points, and then maybe I can remove them in constant time. Well, certainly I can remove them in constant time, and maybe I can pseudo-triangulate this gap in constant time. Well, it turns out we cannot, because the size of the gap is not actually constant. So there may be a linear number of points on one of these concave chains, but it turns out we can pseudo-triangulate such a gap in time logarithmic of the number of points on those chains, and this is good enough. Okay, so but in order to make this work, we first need the pseudo-triangulation, and we were given a triangulation. So we need some way to simplify a red point in time linear in its degree. Okay, so we have a red point which has too many neighbors, and I want to simplify it, and the property that I'm going for is that the number of blue neighbors should not be more than the number of red neighbors plus maybe some constant. Okay, so maybe this is my situation in the input. I look at one red point and all of its neighbors, and it has more than a constant number of neighbors. Some of its neighbors are red, and most of its neighbors are blue. And I want to turn this into a situation where I have right now 1, 2, 3, 4 red neighbors. So I should have at most 4 plus some constant number of blue neighbors. So how do we do it? Well, we first remove all of the red-blue edges in this local configuration, like this. So now I have only red edges, but it's not really a pseudo-triangulation because, well, right here, for example, this red vertex is convex, or this red angle is convex, and also inside here there are some blue convex angles. So I need to add some edges back, but I want this property that there should not be too many more blue neighbors than red neighbors. So how do we do it? So I add edges to all the blue neighbors of the red edges, like this. So for every red edge, I add at most 2 red-blue edges, and sometimes fewer, because these red edges were already neighbors, which means that this is already a triangle and therefore also a pseudo-triangle. And then for the remaining part here, I just compute the convex hull of this blue chain here, or convex path, and I do the same here. So this is now convex, and this one here was already a convex chain. And then inside these regions that I create, I may have some polygons that I still need to triangulate, but this is fine because these polygons only have blue vertices, so I can just triangulate them, and they're already fine for the output triangulation, so I can spend as much time on them as I want. All right. So how much time did this take? Well, it was linear time to remove all those edges, and then yeah, I added some edges near to the red edges, which took constant time per red edge. And then I computed these convex chains, and maybe I pseudo-triangulated, I triangulated some of these gaps, which means that this took linear time in the degree of this red point that I simplified. All right? So I can do this to all of my red points, and then I have a pseudo-triangulation. But we then also still need a way to remove a constant degree red point and re-pseudo-triangulate the gap. Okay? And this is maybe the more tricky part. So let's say my red point has at most 5 red neighbors, so there must always be a red point with at most 5 red neighbors, because the red-red connection graph is planar, so we must have this property. And if a red point has at most 5 red neighbors, then it has at most a constant number of neighbors in total, because we just ensured this property that no point has many more blue than red neighbors. So we can always find such a point. Now the question is, what do I do if I want to remove this point and re-pseudo-triangulate the gap, right? Okay, so we're going to do this in log B time, where B is the total complexity of the edge of this region. So the number of blue points on all of these concave chains together is B. And in log B time, we can re-pseudo-triangulate this gap. So how do we do this? Well, we first just remove the red point and all of its edges. And now we have some region here which has order B complexity. We compute the shortest path between all the remaining red points. So we have now 4 red points on the boundary. And I compute the pairwise shortest path between all of these pairs of red points. There's only constantly many. How do we compute such a path? Well, for this we need to do some tangent queries. So this chain of blue points here may of course have order B complexity, and I have to compute this query that says, well, given this red point, if I sweep a line, which blue point do I hit first? But for this, there are known data structures that can solve this in log B time. So we use those, and then we can compute these shortest paths in log B time for all pairs of red points, and then using them, we compute a pseudo-triangulation of the red points. But of course, some of the outside gaps may not be pseudo-triangles yet. But for those new faces, we can just compute a new pseudo-triangulation. I think even in constant time now, because we don't have to do any tangent queries, we just have to no, I think we do have to do constant tangent queries. So this also takes log P time. So for example, from this red point, I compute the tangent to this curve. Or from this one, I computed it to this curve. And then we get a new pseudo-triangulation. Okay? So this takes log B time. So now what's the global strategy? So first we turn our triangulation into a pseudo-triangulation. Then we search for a constant degree red point. We remove it and we re-pseudo-triangulate the gap. And we keep doing this until there are no more red points. And then, of course, at the end we have a triangulation of the blue points. In fact, not a pseudo-triangulation, but a triangulation because all the pseudo-triangles that we maintain in this procedure have a red tip. If there are no more red points, there are no more pseudo-triangles. But how much time does it take? Well, so one way to analyze it is to look at the running time, is to group the red points we remove into phases. So let's say in the first phase, there's some constant fraction of red points that we can remove. So we are removing all of the red points which have degree lower than a given constant. This means we can find a set of independent red degrees of some fraction, at most 1 over f times the total number of red points that are left. So we remove this 1 minus 1 over f fraction of red points. And this takes time. In the worst case, each of these red points has exactly this 1 over k fraction of blue points in its neighborhood. I mean, of course, it's possible that one has many blue points and the others have few blue points, but that's that's faster than if the blue points are nicely distributed over all the red points. So in the worst case, we get this k times log n over k time to execute one phase if k is the number of red points that are still left. Okay? So this means, so how many phases are there? Well, if we want to remove all the red points and we're removing this factor f of them in every phase, then we get log base f of n phases. And after every phase, the number of red points that are left are, well, n divided by f, divided by f, divided by f, divided by f, I times, if we are in the ith phase. So this means after the ith phase, k will be equal to n over f to the power I. Okay, so now we can fill this in. So the total running time is the sum over all the phases. So there are log base f of n phases. So we sum I from 1 to log base f of n. And the time it takes to execute one phase is, well, this time, k times log n over k, but k equals n over f to the I. So this becomes n over f to the I log f to the I. Okay, so we can just compute this. So f is some constant. And this expression now only depends on this constant f. So if you do the math here, I'm sure you already all did this in your head, and you see that, yes, indeed, this is just a fancy way of writing O of m. So the total running time is linear, and we're happy. Okay? Any question about this problem? Right. So we now know how to, in linear time, compute a triangulation of only the blue points if we're given a triangulation of red and blue points. So now how do we use this to solve our original problem? Well, actually, now that we know how to do this, the original problem is actually not so hard to solve. So remember, we were given our set of regions, which are disjoint polygons in the plane. So something like this. And what we want to do is compute some structure such that later, when we get one point inside every region, we can triangulate those points in linear time. Well, maybe it's already you already have an idea of what the structure could be. The structure is a triangulation of the vertices of the region. Okay, so we have this set of regions, and in our pre-processing phase, we simply look at all the vertices of these regions, and we compute some triangulation. So the edges of the region are going to be in the triangulation, and then I just add some other edges to triangulate this. So of course, computing this triangulation of the regions takes n log n time, but that's fine because we're pre-processing and we have time to spend. And now this is our magic structure H. So it's just a triangulation of the vertices of the regions. And now later we get our set of points P. So what are these points? Well, they are one point inside each of these regions. And now the idea is we just add these points to our triangulation. So for this we have to locate them in the triangulation and add them to the triangulation. And you may think, well, point location takes log n time, so this will take n log n time. But that's not really true, because we can just store in the pre-processing for every region the set of triangles that covers this region, and then we can do point location in linear time. So we locate every point in the triangle where it is and connect it to the three vertices of this triangle. And we get something like this. And this is now a triangulation of red and blue points, so we can forget about the regions. We have a triangulation of red and blue points, and we want a triangulation of the blue points. Well, we just saw how to do it. So we use this algorithm, and we get our triangulation of just the blue points. And this took only linear time. Okay? So that's the whole algorithm. So once we know how to solve this last phase of how to compute the triangulation of blue points given a red-blue triangulation, the rest is fairly straightforward. And this works for the requirement that the regions are disjoint is necessary because, well, if all the regions overlap each other, then there's obviously nothing you can do to preprocess the points. The requirement that they are polygonal is not necessary because you can always, if they're not polygonal, draw some polygons around them, and you get slightly bigger regions that are still disjoint, and you can still do the same thing. Okay. Any questions about this first problem? Yes. Okay, so in principle, if we want to add these blue points into the red triangulation, we have to find out for every point in which triangle it is. And if we would just use some point location data structure, this would take log n time. However, we know, because we preprocessed this triangulation, we know which vertices belong to which region. So we can add a pointer from every vertex to the region, and conversely from the region to the points that make up this region. So now if I get a point in this region, I only have to look at those vertices that make up this region. And now the triangulation of this region is actually just a tree structure. So if I get a point in this region, well, actually, if I get a point in this region, the easiest thing to do is just start looking at some triangle of this region, and then look, well, is my point in this triangle, yes or no? And I look in all the triangles in this region, and then I can find the point in time proportional to the number of triangles in this region. But since the total number of triangles is linear, this still takes linear time. Okay? Yes? F here. F is some constant. It's the fraction of points we can remove. So the idea is if I have some triangulation, and in every triangulation, at some point I have k red points left, and now I want to remove some of those red points which have small degree. How many can I remove at the same time? And it turns out that there's always some constant fraction of red points f, some constant fraction f of red points that I can remove because they're independent. So in a way, f is the size of the smallest possible independent set in the red-red connection graph. Okay, and this is a constant. Yes? Yeah, so n is the total complexity of all the input regions. Sorry, I should say this, yes. So, yeah, yes, of course. So if the complexity is much higher than the number of regions, then the running time will depend on the complexity of the regions, not on the number of regions. So yes, this is good to mention. So n is not the number of imprecise points, it's the total complexity of the imprecise points. So of course, if every imprecise point has constant complexity, then this is the same thing, which is usually the case. But if it's not, then it depends on the complexity. In principle, you can, as long as the region has constant description complexity. Mm-hmm. Yeah, then it's the... Yes. Yes, so it's the complexity then of the polygons that you need to cover these regions. Yes. questions? Okay, then I think we move on to the next problem. We are not in the last slide. Preprocessing onions. Okay. So for this problem, I'm going to talk a bit about onions. For those of you who don't know, if P is a set of endpoints in the plane, like here, then the onion layer decomposition of P, or in short, the onion of P, is the convex hull of P, but recursive. Okay, so I take the convex hull of P, like here, and now I look at all of the points that are not on the convex hull, just this smaller set of points here, and then again I take the convex hull of those points. Okay, and recursively I keep doing this. I take the convex hull of the remaining points, and this is a single point, so the convex hull is just a single point. And this set of nested convex polygons is the onion layer decomposition, or in short, the onion of P. Okay, onions have many applications in many geometric algorithms, and they're very useful. So the question is now, can we actually compute them efficiently in this preprocessing paradigm? Okay, so the onion preprocessing problem, just to reiterate what the problem looks like, we're given a set of n disjoint regions, and for this problem I'm going to assume they're unit disks, because this problem is harder than the previous one, so we need simpler regions. So here are n disjoint unit disks. Well, they're supposed to be disjoint. These ones don't look very disjoint, but they should be disjoint. And the preprocessing algorithm says, again, compute some intermediate structure H. We don't know what it is. Some structure, and then later we get precise points, and we want to compute the onion of these precise points using H faster than n log n time. Okay, so again, the onion can be computed in n log n time, and we want to do it faster. Okay, so we are going to show how to do it in n log k time, where k is the number of layers in the onion decomposition. All right, so the preprocessing algorithm is going to be, we have this set of n disjoint unit disks, and on this set I will compute some sort of a subdivision, a spatial subdivision tree. Okay, so first we observe that there always exists, for such a set of disks, a line that intersects not too many disks, and that has roughly half of the disks on each side of the line. Okay, so intuitively, if you have a bunch of unit disks and they're disjoint, then I should be able to separate them by some line, and if I don't pick the wrong orientation, then the line shouldn't intersect too many of them. So a line like this, it intersects only two disks, and there are a constant fraction of disks on this side and a constant fraction on that side. And this is indeed true. You can compute such a line that intersects at most square root of n log n disks by, as a result, by Alon et al. And we will use this to iteratively subdivide our disks into a tree structure. Okay, so we take one such line, and then on both halves of the line, we include this disk on this side and on this side, and then we recursively apply the same lemma. So on the left and on the right, we compute another line, and then again, we subdivide the smaller regions, and then we subdivide them again and again. And eventually, we get a tree where in every leaf there is only a single disk. And a disk may appear in multiple leaves, but every leaf has at most one disk. And because of this lemma that says every line doesn't intersect too many disks, we can prove that the total complexity of this tree is still only linear. I needed one more level because these were not yet separated. So we call this tree T, and well, we claim that T has a linear number of leaves, and the depth of T is only log n plus some constant. Okay, so the number of times I have to subdivide one side until I get only a single point, a single disk in my leaves, is not much more than logarithmic. Okay, so we can create this tree. Why is this interesting? Well, this tree is actually our magic structure H. So, okay, so in this case, H is the tree, and in the pre-processing, we don't do anything except for compute this space division tree on our set of disks. Okay, takes slightly more than n log n time to compute this tree, but it's the pre-processing phase, so we don't really care about running time. The main question is, how can we use this tree to compute the onions faster than in n log n time? Okay. So the reconstruction algorithm. Suppose I have my set of disks like this, and I have this tree, and I get a set of points in my disks. How do I compute the onion of those points? Well, the first thing to do is to locate those points in the disks and therefore in the tree. But again, I can just store a pointer from every disk to the leaf of the tree they are in. So this we can just do in linear time. So I have a set of points, and I know where they are in my tree. And the idea is that I'm going to recursively compute the onion by first computing the onion of every point set in the leaves. Well, if a leaf has a single point, then the onion is just the single point itself. And then recursively, I go up the tree, and for every pair of siblings, I compute the onion of the point sets of those two siblings together. So first, well, if there's any empty leaves, we can remove them. Of course, there can be empty leaves because one disk, if you remember, could intersect with multiple leaves. So remove all the empty leaves. And then for any pair of neighboring onions, we unite them. Okay, so we go one level up the tree, which means we remove some of these edges, which means now we have two onions that are in the same cell, and I want only one onion per cell, so I compute the union of these two onions. Okay, how do we, what does this look like? Well, if these are single points, then the union is just going to be a segment. So now I have some segments and maybe some still single points in my tree, and I just go up the tree, I remove again these edges, and I compute the unions of my onions. Right now they're still all convex polygons, but if I go one more level up, maybe I get some onions which have multiple layers, and I go another level up, and another level up, and another level up, and in the end I've computed the onion of my entire point set. Okay, so that's the idea. Of course, the question is, how much time does this take? And for this, the main thing we need to know is, well, how do we actually unite two onions? How do you compute the union of two onions? Okay, because we do this in every step. How efficient is it actually? Okay, so we need to solve this sub-problem maybe of computing the union of two onions. So how do we do this? Well, we have two onions, and I want to compute their union, so the onion of the union of the 2 point sets. So the observation is, if I have 2 onions already and the total number of points in those 2 onions is n, then I can find the convex hull in log n time. So I can find the outer layer of these onions in log n time. And how do I do this? Well, again, using the same kind of tangent queries that we saw in the previous topic. So we can build a data structure that allows us to compute the tangent between these 2 outer layers, and then this gives me the convex hull. I can compute it in just logarithmic time. And now the idea is, well, if I compute this convex hull, now I only need to find the onion of all the points inside here. So I just remove the convex hull, and I'm left with this. So this is not really two onions anymore. That's a bit of a problem. So I cannot just recurse and again compute the convex hull, because if I compute the convex hull of the next two layers, maybe I get this edge here, which doesn't include this point. So I might miss something. So these are two, let's call them half-eaten onions, and we cannot compute their convex hull, so I have to restore them. So I want to take one of these half-eaten onions and turn it back into a proper onion. Okay. So for this we use onion restoration and unification algorithm. So we have two of these onions that are not proper onions anymore, but we can compute the convex hull of one of these guys in log n time, okay? Because this guy consists of one onion and half of a layer of an onion. So I can compute the tangent from this endpoint to this onion, again, in logarithmic time. Okay, so we get these two convex hulls of the individual onions. And now we remove those, and then we observe that what we're left with inside is again a half-eaten onion. So this is some onion and half of one layer. So again, I can compute the convex hull of this in log n time, like this. And then after this, I'm left with another half-eaten onion in here. So I have this half chain and a single point. And again, I can compute the tangent from this point to this onion, which is a single point, in log n time. Okay? So I do this, and now I have two proper onions. And now that I have two proper onions, I can again go back to the previous step and compute the convex hull of both of the onions, like this. And this is the second layer of the union that I wanted to compute. So I set this aside and remove it, and I'm left again with two half-eaten onions. And I restore those onions using the same procedure as before, like this. And now I have two proper onions again, and I can take their convex hull. I get the third layer of my union. I have two of these half-eaten onions. I restore them. I take the convex hull. I do the same thing once more. I take the convex hull. And now I have 1, 2, 3, 4, 5 layers of the onion. So how much time did this take? Well, if the total number of layers here is k, then this took k squared log n time. Okay, why? Because computing one of these outer convex hulls took log n time, but then to restore the two onions, I had to recompute their layers k times, and every time took log n time. So it actually took k times log n time just to compute one of these layers. And I did this k times, so the total running time here is k squared times log n. Okay, still k squared times log n is reasonably efficient, especially if the onion doesn't have too many layers. Okay, it's faster than the n log n time that it would take to compute it from scratch, as long as k is smaller than square root of n, bigger than square root of n. Okay? So this is how we unite two onions. Okay, now then we just have to plug this back into the overall algorithm. So for the final result, we have this set of unit disks, which we can split and turn into this tree T, which takes n log n time. And then we can unite onions pairwise in k squared log n time. And using this algorithm, we can reconstruct the whole onion in n log k time. So why is it n log k time? Well, we have at most n levels in our tree, and for every level we have to compute this union of this onion, but at the bottom levels the number of points inside each leaf is so small that we just use a brute force algorithm to compute the onions in, well, let's say m log m time if there are m points in this layer. And at some point, once the number of layers in our onion becomes sufficiently small compared to n, we switch to using the other unification algorithm, and then we do the math and we get this n times log k running time for the final algorithm. And this is not always faster than n log n, of course. If the onion turns out to have a linear number of layers, well, then this is not faster than computing the onion just from scratch. But in this case, we also have a matching lower bound that says we cannot do anything better than compute it from scratch. But if the onion has fewer layers, then it works in n log k time, which is faster. Okay. Any questions about onion preprocessing? Yes.
If we have an early point.
If we have, sorry?
If we have an early point, is it valid?
I'm sorry, I'm not sure I understand the question. Okay. Any other questions? Okay, then I think we have some time to go to the third problem I want to talk about as well. That's right? I still have time. Yes, okay. Okay, so let's talk about preprocessing for Delaunay triangulation. So in the first topic, we saw how to preprocess a set of points to compute a triangulation of the point set. Now we want to not compute any triangulation, but a specific one, namely the Delaunay triangulation. Okay? So everybody knows the Delaunay triangulation? Okay. Then, of course, it's harder to compute the Delaunay triangulation than a normal triangulation, than any triangulation, because it's a specific one, but you can still compute it in n log n time. And still we want to compute it faster. But because it's harder, it only works for more restricted types of regions. So here also we will assume the regions are unit disks. And in fact, if the regions would be arbitrary polygons, then we can show a lower bound that shows this is not possible, and we need n log n time even after any kind of preprocessing. But for unit disks, we can preprocess them and compute the Delaunay triangulation in linear time. So I'll try to give an idea of how this works. For this one, I don't think I can give all the details, but hopefully give a bit of an overview of how it works. So first we will define the concept of expanded Gabriel disks. Okay, so if you have 2 points, P and Q, then the normal Gabriel disk of P and Q is simply this disk, right? It's a disk that has P and Q on opposite sides of the disk. And we call it CPQ. And the expanded Gabriel disk is simply the same thing, but we increase the radius by 2. Okay, so this here is the expanded Gabriel disk, and I call it C plus of P and Q. Okay. Lemma about expanded Gabriel disks. If no point lies inside C plus of P and Q, then P hat Q hat is an edge of T hat. Okay, so what does this mean? I'm using lots of notation here that I didn't define. So P is my set of disk centers. Okay, so P and Q are imprecise points because they have a unit disk around them. And P hat and P and Q hat are going to be my real points. Okay, so I'm going to have some real point P hat that's within distance 1 from P. I'm going to have some real point Q hat that's within distance 1 from Q. And I want to compute the Delaunay triangulation of the points with hats. And I call this T hat. Okay, so I get these disks here around P and Q. These are unit disks. And inside these unit disks, I get my real points at some point. So these are the points of which I want to compute the Delaunay triangulation. And so my lemma here says that if this green disk doesn't contain any other point, then I will have an edge between those two red points in my Delaunay triangulation, basically because this red circle here through them must be empty. If this red circle is not empty, then it must be because there's another red point inside this circle, but then this red point must be inside an imprecision disk, and the center of that imprecision disk must lie inside this green circle. In the worst case, this red circle could correspond with the blue one, and then this point could be exactly on this green edge, but it cannot be outside. Okay? So if there is no point inside this green disk, then I know for sure that I have an edge in my Delaunay triangulation. Okay, so then the idea is to find maybe these green disks for all my pairs of imprecise points, and then just look for the ones that don't have another point inside them, and then I know for sure that those pairs must have a Delaunay edge, so those I can just pre-compute. And if I'm lucky, then maybe this gives me already the whole triangulation, and I'm done. Of course, I probably won't be lucky. Okay, so in the preprocessing, we will compute a minimum spanning tree of the imprecise points. Okay, so the minimum spanning tree we just compute on P, so on the centers of the unit disks. So we have our set of centers of unit disks, and I just compute the minimum spanning tree. And for every edge of the minimum spanning tree, I compute this expanded Gabriel disk. Okay, so I get, for every edge, I get one of these disks, and this edge here has this disk, and I get this big mess of disks in total. But we can already see that for some of them, like this disk here, it doesn't contain more than those 2 points. But some of them, like this disk here, for this edge, it does contain another point. Okay? And now I will just store for every expanded Gabriel disks a list of all the points that are inside this disk. Okay? And we prove that the total complexity of all of these lists is just linear. So even though there's a linear number of Gabriel disks and a linear number of points, and in principle one disk could contain a linear number of points, because we take the minimum spanning tree, we can prove that the total number of points in all of these lists together is just linear. And now the approach is going to be, well, if I now get my real points, I'm going to locally connect the points along these edges of the minimum spanning tree. And if it so happens that there are no points in this disk, then this is easy. I can just compute the direct connection. But if there are points in it, then I may have to do something more clever. But the point is that I only have to look at the points inside this disk to do the more clever thing. Okay, so what is this clever thing that we're going to do? Well, let's phrase it in independent terms. So given a point set P and its Delaunay triangulation and some circle C. Okay, this is any point set, any circle. Then an edge of the Delaunay triangulation is certified by this circle C if there is an empty circle that supports the edge that lies completely inside this circle. Okay, so those edges are certified by C because the edges lie completely inside the circle, and for each of the edges I can draw an empty circle that lies inside C. So these are the edges that lie completely inside C, and those that are certified are those for which I can draw an empty circle in C. So for example, this is an empty circle, which means this edge is certified, and this edge is certified, and this edge is certified. But this edge here is not certified by C because if I draw an empty circle that doesn't contain any points in here, then the circle doesn't lie completely inside C. Okay? So this edge is not certified, so we don't have it in our set of certified edges, and also similarly these edges are not certified, but these are certified. Okay? And we claim that the graph of certified edges inside such a circle is connected. Okay, and why is this useful? Well, it's useful. I'm actually going to prove this lemma. So, proof of this lemma, why is this connected? Well, just take any point in here and look at the center of the disk and start growing a small circle towards the center of the disk until it touches another point. And then, because I started growing from an empty circle, this must give me an empty circle that lies completely inside C that connects 2 points. Okay? So for every point I can do this, and then I can continue growing from the next point until I hit the center of my circle. And then I just keep growing until I pass the center of my circle and I hit some other point. And I find another edge. And from there I go to the center of the circle. And well, here, so I find the same edge again, so I stop. And I do the same thing starting from some other point that I haven't connected yet. So I start growing towards the center. From here I start growing towards the center. From here I start growing towards the center. And from here also. And since I can do this for every point, I always end up with the same point, namely the one closest to the center, which is this one. And this means that this graph is connected. Okay? All right. So why is it useful that this... yes, sorry? Here, this is the empty circle. Okay, so this, and it's still an empty circle because there are no. Oh, sorry, maybe. Okay, yes. So yes. So in a Delaunay triangulation, every triangle of the Delaunay triangulation has the property that the circle through the 3 points is empty, but every edge has the property that there's a circle through the 2 points that's empty, and every pair of points that has such a circle is an edge of the Delaunay triangulation. Mm-hmm.
We cannot have such edge because I just consider the circle which is made by 3 points.
Right. Yeah, so this edge is not certified and this one is not certified, but this one is actually certified. And because of this, actually, we know that at least one of those edges must be in the Delaunay triangulation, but we don't know which one. Okay? Okay, so why is this useful? The fact that this graph is connected? Well, remember we computed this minimum spanning tree of P, and now for every pair of points in this minimum spanning tree, we want to reconstruct some part of the Delaunay triangulation that connects those points. We do this by processing the tree by increasing length of their edges. Okay, so suppose we have some pair of points and their their expanded Gabriel disk, and there's some other set of points whose centers lie in this disk, and we pre-computed this list. Now what we want to do is connect this point with this point, or compute some part of the Delaunay triangulation that connects them. So how do we do it? Well, we compute the set of real points, and maybe we don't know for sure that there is a direct edge between those points, but we know that there is some path in the Delaunay triangulation that connects this point with this point by this lemma that we just proved, right? Because the red points is some set of points inside this disk, and it has this property that we can find this path of certified edges. Okay, the only question is how do we find this path? So if PQ is a short edge, then the number of points in here can only be constant by a simple packing algorithm. Argument. There cannot be too many disks, unit disks inside this green disk if the disk is small. So we can just do this in brute force. So if it's short, no matter how many points are there, we just draw all the real points and compute the Delaunay triangulation, and we just check which edges are certified, and we look for some path in this graph, and this just takes constant time. Problem is, not all edges are short. If the edges are long, then we cannot do this directly, and then we have to do a more careful argument that still takes only linear time in the number of regions, disks in this region. And here the idea is that because PQ is an edge of the minimum spanning tree, we know there are no other points inside this loon shape here. But there may be many other points here and there. And now we want to find some connection from P to Q using some Delaunay edge from some point up there to some point up below here. But there may be quadratically many of them. However, we can still solve this problem. So we know by the property of the minimum spanning tree that all of these red points are already somehow connected, and these red points are already somehow connected. So we just need to find some pair of points to connect, and we can grow a circle from the center until it touches one point, and then we grow another circle until it touches a point, and then we find an edge between them, and this gives us a connection between P and Q. Being a bit fast here about the details, because I think we are out of time. But using this, we can now compute the whole Delaunay triangulation by taking our set of points, computing this minimum spanning tree, processing the edges from short to long. So we have our real set, the red points. We take one of these Gabriel disks, and we compute this Delaunay triangulation, and we keep going with the next shortest edge. And at some point, so for every edge we process, we make sure that P and Q are connected in the Delaunay triangulation. And then, if we've done this for all edges, we have some connected subgraph of the Delaunay triangulation. And from this, we can reconstruct the Delaunay triangulation in linear time by using linear time triangulation by Chazelle, and then compute the constraint Delaunay triangulation by Chen and Wang. And this is all linear time. And we are done. Okay. Went maybe a bit fast in the end, but are there any questions? There are questions, but no time to answer them. Okay, well, thank you for your attention. I showed some applications of the preprocessing paradigm, and hopefully this gave a different perspective on how you can deal with uncertainty.